When you watch a photorealistic 4K video, battle another player across the globe in real time, or prompt an AI to write a poem, it feels like the machine on your desk possesses some kind of vast, innate intelligence. But beneath the glass and metal, there is no comprehension. A computer possesses exactly zero understanding of mathematics, color, or the English language. The entire foundation of modern technology relies entirely on just two physical states: a high electrical voltage, usually around 5 volts, and a low voltage of 0 volts. That is the entire vocabulary of a computer: current or no current. To process information, engineers use digital logic to translate these two voltages into binary code. A high voltage represents the number 1, and a low voltage represents a 0. Every single piece of media you have ever consumed on a screen boils down to billions of tiny components, making one single simple choice over and over again: true or false. The physical components making these true or false decisions are called MOSFET transistors. They act as microscopic electronic switches that physically open or close to change the voltage. When engineers wire specific combinations of these transistors together, they create what is called a logic gate. A logic gate is a tiny circuit that receives input voltages, follows a strict mathematical rule, and spits out an output voltage. This diagram illustrates the first rule, the AND gate. It is incredibly strict. The AND gate only outputs a 1 if every input is a 1. Conversely, the OR gate outputs a 1 if at least one input is a 1. Finally, the NOT gate simply reverses whatever signal comes in. By passing voltages through these specific physical structures, we create the complete fundamental alphabet of all digital electronics. Once you have the basic alphabet, you can build more complex rules. Take the exclusive OR, or XOR gate. Its rule dictates that the output is high only when the two inputs are different from one another. This specific gate is critical because its behavior perfectly mirrors the mathematical rules of binary addition. Let's look at this logic circuit in action. By wiring an XOR gate and an AND gate together, engineers create a half adder. If you feed it two 1s, the gates route the electrical currents, outputting a 1 and a 0. By chaining thousands of these adders together, you build an arithmetic logic unit, calculating massive equations in fractions of a second. The processor is never actually doing math in the human sense. It simply routes electrical currents through complex labyrinths of logic gates that simulate mathematical laws. But a system that calculates instantly isn't useful if it instantly forgets the result. Standard logic gates only hold their state as long as the current is flowing through them. To solve this, engineers created a special configuration called a flip-flop. This diagram shows how a flip-flop loops its output back into its own input, trapping the electrical signal in an endless cycle. It remembers its state. When you group millions of these flip-flops together, you get registers and RAM. This is how fleeting electrical voltages are captured and stored as permanent digital memory, turning temporary pulses into your saved photos and documents. In the early days of computing, storing this data required massive, room-sized mainframes packed with large physical relays and vacuum tubes. Today, a modern CPU compresses billions of these arithmetic logic units and memory registers into a piece of silicon smaller than a postage stamp. These layers of logic aggregate into instruction sets, the physical language that software uses to tell the hardware what to do. By stacking billions of these tiny decisions in synchronized sequence, a machine bridges the gap between raw voltage and the high-level complexity of modern artificial intelligence. Despite their incredible speed, these systems are still bound by the harsh physical constraints of manufacturing. Modern processors are built using CMOS technology, etching complementary MOSFET structures into actual physical silicon wafers. To keep everything running smoothly, the entire system relies on a clock signal. This acts as a microscopic metronome, sending out timing pulses that force billions of separate gates to switch states at the exact same moment. However, these physical switches are not infinitely fast. Because it takes a tiny fraction of a second for electrons to travel through a gate, systems experience propagation delay, placing a hard physical limit on how fast a processor can run. As you force billions of transistors to switch on and off billions of times per second, the electrical friction generates immense heat. Without robust thermal management and cooling systems, the chips would melt themselves down. Now, humanity is engineering logic gates so small they approach the atomic scale. At this microscopic level, the physical barriers holding the electrical current become so thin that an electron sometimes just quantum tunnels right through the wall, defying classical physics and causing data errors. Our digital world rests on the physical management of billions of switches, etched into silicon at a scale where the movement of a single electron can change the result. It is a massive synchronized architecture built to survive the heat and quantum leakage of its own operation.